Hello, my friends. Welcome to Origins. I'm Don Chapman, and I'm your host. It's great to have you with us today. Origins is a forum where we take the evidence of science and use it to confirm the truth of God's creation. We usually do that by bringing in some guests who are experts in the various fields of science and apologetics and have them share with us the truth that God revealed to them. We've got a great guest with us today, Dr. Jerry Bergman. The thing I love about Dr. Jerry is that he is a lifetime student. He told me he has 9 different degrees from the college level up, including several PhDs. He's been a student all his life. You know, learning's not something you do to get a degree. Learning's something you do because you want to pursue the truth. And that's what Dr. Jerry's done all his life. Dr. Jerry Bergman, welcome to Origins.
Thank you.
It's great to have you here today.
Good to
We're going to talk about mutations today.
Right.
We've been joking about this third ear that I have under my arm and how I grew it through mutation. Is that what this is about?
Well, it's about actually the harm that mutations cause.
Okay. Now, mutations, when we think about it, you can't go very far into talking about serious macroevolution without talking about mutation as the vehicle. Is that true?
Yeah, the basis of evolution is mutations. That's what evolution is based upon. That provides the raw material for natural selection to select from, according to Darwinists. And I've got a couple quotes which I think are very telling about what Darwinists believe and how important mutations are. If I can
Let's do it.
Go up here. And as I mentioned here, the primary basis of macroevolution, and macroevolution is what we're talking about here, and macroevolution is evolution beyond the species level, from, as they say, from the goo to you by way of the zoo. That's macroevolution. And mutations are basically variations in the code that produces you and I. And the code, of course, is well known as the DNA code we see over here. This is a model of DNA. And the DNA code is made out of letters. And these letters can change. And the changes are what Darwinists postulate produce the variety which natural selection can select from. So they change the protein coding DNA. That affects the phenotype.
You're saying that the DNA chain is made up of letters.
Right.
It's not really made up of letters. It's made up of chemicals, but it's almost a chemical language, isn't it?
Right. It's made out of chemicals, and we just, instead of saying the chemical, because they're long names, so we just
assign them letters.
Assign them letters, right. We just T and A and G and C.
And so there's really a language written in chemicals.
Right.
Okay, that's great.
True. And, of course, there are other sources of variation. We're not saying mutations are the only source. Sexual reproduction, for example, you have 10 kids. They're all different. That's a source of variation. Crossing over, genetic crossing over, is literally where the chromosomes exchange parts before they produce a human being. And this exchange basically allows new traits to appear because the combination changes because of this crossing over. When I explain this to my students, it's like you lay down next to someone and your legs are literally cut off in exchange. So you end up with their leg and they end up with your leg. So you have a difference because of this exchange. And this is crossing over. Transposition is another source of variety, and transposition is literally where the genes cut themselves out and go somewhere else. And therefore they change the code, and therefore they change the pattern, and therefore they change the phenotype, the traits that result. So there are other ways of producing variety. But all this does is rearrange the existing information. You don't have any new information. You basically have information that's there, which is shuffled around. A good example would be you rearrange the furniture in your house. You have, looks different, but of course there's nothing new.
And I think it's really important that we camp there just a minute, because if evolution's going to work, there has to be new information.
Right.
And as you said, it doesn't matter how many different ways I arrange the furniture in my living room, we're still going to have that old couch somewhere, and there's never going to be a new couch.
Exactly.
And that's exactly what you're saying about the DNA. There are ways that God has made for there to be variety within that species or that kind, but there's no way to have a new kind in there, is there?
Exactly, and that's the problem. And
Thank you, Fred. That's great.
They recognize that, Darwinists do. That's why Ernst Mayr, who's a picture up here, he just turned 100, by the way, recently. And he said, ultimately, all variation is due to mutation. And this is not a minor figure in Darwinism. He's one of the leading, if not the leading, evolutionary biologists in the world today.
All their eggs are in the mutation basket.
Right.
Okay.
That's critical. And
all right.
Theodosius Dobzhansky, likewise one of the leading evolutionists today, said the process of mutation is the only source, he stresses, only source of the raw material and hence of evolution.
So if we can show that mutation doesn't make evolution happen, the evolutionists themselves would say then evolution can't happen.
Right, exactly. That's why this is such a critical area.
All right.
And a good illustration of this is Dawkins, Richard Dawkins, who's also one of the leading evolutionists today. He lives in Great Britain. He teaches at a major university there. And he developed a computer simulation where essentially he took this sentence, "Me thinks it is like a weasel," and this is taken from Shakespeare, and he started out with random letters. These are all random letters. You just generate randomly. And then he developed a computer program that would change these letters one at a time. And the changes, if they met this goal, they were saved. For example, the first here is a W, which of course is not the first letter here. It's an M. So here we have a mutation which produces an M, and then the M, therefore, is saved, and you can see from that point on, the M is retained in the program. And eventually, if we keep doing that, eventually we get to the sentence, which is, "Me thinks it is like a weasel." And that's an illustration Dawkins uses to illustrate basically how Darwinism works, how evolution works.
You know, I'm hearing you say that, and I understand, I think I understand at least how that happened, but with a computer, there is a source of these letters coming in. A man is not a computer. We don't have an influx of new letters, so is that a valid analogy?
Well, there are a lot of problems with it, and of course, creationists like to use it because it's a good illustration of the problems of Darwinian idea. Dawkins uses it to show how Darwin works, but we use it to show how it cannot work. Okay. Among the problems that exist with mutations as a source of variation are we assume mutations are random, and of course, that's a major assumption. And as we'll show, the problem is we know they're not random. When random mutations occur, certain amino acids are far more likely to be produced than others. So we'll assume for a minute they are random. So we'll just take that as an assumption. But we're going to end up with certain amino acids are far more likely to be produced than others. And of course, these letters, these A's, T's, and so on, they produce amino acids. Amino acids are assembled to produce protein, and protein are the building blocks of you. You and I are made out of protein. And therefore, we get the protein by getting these amino acids. So to produce the protein, to produce you and I, we have to have the right order of amino acids. So it's critical to get the right order of amino acids. And random combinations, I point out here, are more apt to produce certain amino acids. And I'll show you from the following table why that's true. For example, this combination, TCT, here, you can see that plus a TCC and TCA and so on. There's 6 different combinations, all which produce serine. Okay, so we have 6 different combinations. So if we randomly shuffle the 4 letters, we will get 9.4% of the shufflings will be serine. Okay, now we'll go over here and we'll look at tryptophan. There's only one combination of amino acids that produces tryptophan. Therefore, only 1.6% of all combinations will produce tryptophan.
So you have almost 9 times as much chance of getting that first result as the second one.
Right. So we'll end up with a lot of serine and not very much tryptophan. Well, that's a problem because we need actually a lot of tryptophan in many different amino acid combinations to produce a protein. And as a result, tryptophan is very important. And by natural means, we're not going to get nearly enough of this, and we'll get way too much of the serine. So we don't get the right combination we need to produce an organism. It's off balance, assuming now they're random. Okay, a basic problem is that the rate of mutations from one base to another base is not equal. So in other words, they're not random. We don't end up with a random change of letters. And one study which I looked at found the totals, which refers to all base pair conversions, as follows. I put that in a chart to make it easier to follow. And this is the conversion to thymine. So the conversion of this G to a T, C to a T, A to a T, we see is a total of 58% of the total of all conversions. So what that means is that all conversions, we're talking about mutations. We call that a conversion. So mutations, basically, what's going to happen is we're going to end up with an awful lot of thymine because all mutation types are not equal. So we'll end up with a huge amount. Well, over half of the mutations are going to end up with thymine. Guanine, on the other hand, only 14% of the total. And cytosine, only 23%. of the total, and adenine only 5% of the total. So applying this now to Dawkins' illustration, you can see what's going to happen is the conversion of thymine is fully 10 times more common than conversion to adenine. And as a result, this is what we'll get. Instead of getting our me thinks it is like a weasel, what we're going to get is a lot of T's, because the T is much more common. Now, of course, some of the T's will convert back to the other letters, but by and large, the T's are going to dominate, so eventually what we're going to get is lots of T's. So we will never, just looking at this fact alone, we'll never end up with me thinks it is like a weasel. We're going to end up with dominance by far of T's.
Now, you used a very dogmatic word there. You said we will never end up with me thinks it is a weasel. Are you saying that it's improbable, or are you saying it's impossible?
Well, it's improbable to the point where we might as well say it's impossible.
The chances become so infinitesimal that it simply couldn't happen.
Right. And there is a very, very low probability, but the probability is so low that we say for all realistic purposes,
realistically, it couldn't happen.
It's basically
so you're
zero.
basically saying that for mutation to be possible, or for mutation to be positive, really isn't possible.
Right, because of this, and there are several other factors too, but this is one factor.
Well, that's interesting. We've got to take a break right now. We're going to talk about hot spots when we get back, so don't go away. This is going to be hot, and we want you to be with us for it. We'll be right back.
Creation versus evolution. You weigh the evidence. Tadpole to toad. Self-destruct DNA. Biologists have found that certain living cells come with a built-in self-destruct mechanism. For example, as a tadpole turns into a toad, it no longer needs its tail. When the special gene gives the order, the tail cells begin to die. In other words, some living cells contain a gene that signal the death of the cell at an appointed time. Why would evolution develop genes that order their own death? By definition, such a gene would not aid survival.
We're back, and welcome back. I'm here with Dr. Jerry Bergman. We're talking about mutations. You know, mutations have to be the vehicle through which evolution works if it's going to work. But Dr. Jerry Bergman is telling me that, in fact, mutations prove that evolution can't work. Now, Dr. Jerry, help us first of all. What's a mutation?
Okay, mutation is a change in the DNA code. This is a model of the double helix you can see here, and you've got two helical circles around here, and inside there you can see those bar-like materials. These are what they call base pairs because they're chemically bases. And these base pairs match up together. We have, for example, T matches up with A and C matches up with G. And these two match up together to produce the code. And the code basically is what produces the amino acid set, which produces protein, which produces you and I. And every now and then, for a variety of reasons, a mistake is made. For example, cosmic ray may hit this and damage one of the rungs, has to be repaired. And it's usually repaired properly, so we're okay. And we have about a dozen repair processes which are constantly monitoring this and repairing it. It's constantly being repaired. This is going on 24 hours a day. Every now and then it doesn't repair it properly. It puts the wrong base pair in there. And so instead of having a C, we end up with a T. So that's a mutation, so we have a change in the DNA pattern. And these are called mutations.
And now, for evolution to work in this modern day and age, obviously when evolution started, they didn't know about DNA.
No, didn't have any idea of any of this.
And so to take that 19th century theory and to see it work in the 21st century, somehow the whole business of DNA has to be included in their thought.
Right, and that actually is where scientists don't accept Darwinism now, they accept neo-Darwinism. And neo-Darwinism is where we've added the information relative to mutations. And they thought this would be a savior for Darwinism, but it's turned out to be the opposite. It's turned out to be lethal for Darwinism.
And one of the big kahunas in the neo-Darwin movement is a guy named Richard Dawkins.
Right.
And Dawkins has written a book showing how DNA could work to produce the mutations needed to bring about evolution.
Right.
And you're saying that it isn't working.
Right. It's from what we know about biochemistry and molecular biology, we understand now it doesn't work. It cannot work.
Now we're ready to talk about hotspots.
Okay. Hotspots are, the mutations tend to occur in certain areas. They're much more common in certain areas. In fact, P53, which is a gene we've looked at more so than many other genes, we find that about 70% of all mutations are only in 3 or 4 areas along the entire gene. And some of these genes could be thousands of base pairs, so many are huge. So there's a lot of areas where a mutation can occur. And if the vast majority occur in a very small area, we know there's something going on. And we understand now some of the reasons.
Do we know why there's hotspots?
Yeah, we understand some of the reasons. It partially has to do with the construction of the double helix, where they're located, because some parts of the double helix are more exposed to radiation or other sources of mutations than others. Certain parts, like when you have a lot of letters that repeat each other over and over, like you have a lot of T's or a lot of G's, that area tends to be prone to a hotspot. Some we're not aware of exactly why there are hotspots, sure. But we know there are hotspots. There are also cold spots. Cold spots are where they rarely occur for various reasons. And one of the most common mutational hotspots is at the CG dinucleotide. And they're involved in mutations in about 12 times more often than other dinucleotide sequences. So this is one example of many. And there are several reasons why this CG tends to be a hotspot, but here I was just trying to show you that there are a number that we know that exist. In fact, in one study, only 2 mutations accounted for 94.4% of all mutations out of 319 identified in one gene. And there are many more that are possible in this gene. There are maybe 1,000 that are possible. But there are 319 they identified, and then out of these only
almost all of them was at just 2 specific places.
2 places, right. Yeah. And so what does this hotspot have to do with Dawkins' illustration? Well, this shows it. Result of hotspot and back mutation. Now, I've combined these together because we have hotspots, and of course, hotspots means that you're more likely to have a mutation in that area, but it's more likely to go forward, to change to a T, for example, but also more likely to go back. So this is why we can occasionally have mutations which repair the damage. We can actually have a mutation and it heals the damage. So we can have, in this situation, a beneficial mutation. So if we take the example again, methinks is like a weasel and you go forward. Of course, what we're looking for now is the M, in this case, the W actually, to change to an M. Okay, and you can see that's not a hotspot, so that never changes. On the other hand, S happens to be a hotspot area, and the T you can see now is what we start out with. So the T changes to a Y, to a T, to a T, to a T. And we end up, because this is a hotspot area, we end up with accumulation of Ts. So what happens when we look at both hotspots and back mutations, plus the tendency to go from a C and a G to a T, we end up with constant changes in a small area of the code here. So we end up with never getting what we want, but we end up with constant changes to a T in the hotspot area.
So those cold spots, they're never going to change. And the hot spots, you're going to keep changing there.
Or the cold spots will rarely change, that's true. And the hot spots will commonly over and over change.
So Dawkins is assuming a uniformity across the letters, and it just isn't there.
Right. For his model to work, you have to have the uniformity.
And that's not true in the DNA code.
Right.
All right. I'm with you.
And the other thing we need to look at is you can't only look at base pairs, but you also have to look at polarity, because bases could be polar or nonpolar or semipolar, because basically these amino acid sets are held together by the polarity. That's a critical aspect in bonding the protein to produce a workable, functional structure. And when we look at these charge differences, we can see that the nonpolar uncharged, just by random changes, we end up with 34% of the amino acid sets are nonpolar uncharged. 28% are polar uncharged. 11% are polar, nonpolar borderline. 12% are polar positively charged, and 6.2% are polar negatively charged. Now what that means is we're not going to, by random chances, we're not going to get the combination we need to produce the protein structure we have to have. And so purely by random changes is not going to work. Now hotspots even complicates this further.
It is complicated. Give me a couple of examples of mutations that you've seen.
Well, my work is in cancer research, and doing cancer research, of course, what we're looking at basically are mutations. Cancer is a result of mutations. That's what causes cancer. Cancer is a genetic disease. And so we basically spend our time studying mutations. So we have a lot of information about mutations. And what we see is they're negative. I've never seen a positive mutation in the thousands that we've looked at in cancer research. They're invariably negative.
So when you see mutations, it's a disease, it's a problem, it's something bad, not something good.
Almost always right. There are a few positive ones, but we understand those. They're not a problem for creationists. But by and large, what we see is 99.99% are clearly negative.
Now, this is a big question, but that's all right. You've done a lot of study. How many positive mutations would it take to get from that goo to you?
Well, people have estimated, it's obviously a guess, one doesn't know.
Sure, I mean, we're talking here in speculation.
But those people who have speculated on this say it takes billions, if not many, many billions. So we're talking about a huge, huge number, and of course if 99.99% are negative.
They're going to cancel out those couple positives that happen.
Right, which is exactly what happens.
And we begin to say that, you know, this whole idea that the whole thing could have happened by evolution, by mutation, it just isn't possible.
From what we understand now, yes, it's certainly beyond the realm of what we understand probability to be.
You know, my whole life I've listened to people and they've equated evolution with science and they've equated creation with religion. And they've said that the scientific world sees this whole thing from a perspective of evolution, and us creationists, we're just these radical religionists who don't look at science. But today you're telling me that science is on the side of creation, and good science simply isn't proving evolution.
Yeah, I know many Christians who became Christians because of their study of science.
Isn't that amazing? And you know, my friend, I want to speak to you for a moment, and I just want you to know that we've got scientist after scientist telling us that when we really put evolution under the microscope, when we look at the evidence that they're giving us, not all, it isn't a creation versus evolution debate. Evolution isn't possible. It just doesn't work. We always come back to the reality that our origin is in God, our Creator. And I hope today's show has helped you to see that this just isn't possible. You know, if you have questions, write to me at Origin, CTV, Wall, PA, 15148, or get on the internet and contact us at www.originstv.org. In the meantime, I just want to remind you that, you know, it's God's view that He created you, and that should be your worldview too. God bless you till next time.
Thank you for watching this edition of Origins. If you'd like a copy of the information presented today, you can download a PDF file of program number 506 from our website at www.originstv.org. For a printed version, send a $5 donation to cover shipping and handling to Cornerstone Television, Wall, Pennsylvania, 15148.